This is the start to Chapter 3, Numerical Summaries of Center and Variation. In Chapter 3, we're going to take a look at the center and spread, compare them between symmetric distributions and skewed distributions. We're also going to look at types of variation, and we're going to look at the empirical rule and z-score. We're going to use box plots, 5-number summary, and outliers, and then we'll compare distributions. This video is just for Section 3.1, Summaries for Symmetric Distributions. We're going to look at the measure of center, which is the mean, and then the measure of spread, standard deviation. Okay, so recall when dealing with numerical data, you need to describe the distribution using 3 characteristics. The 3 characteristics were shape, center, and spread. Also recall in Chapter 3 the specific ways to describe the center and spread. So for shape, we're going to look and compare the difference between symmetric and skewed. And then remember for center, we call it the typical value. And then for spread, we are looking at its horizontal variability. So here's a dot plot that shows the distribution of ACT scores for a sample of statistics students. Remember, a dot plot is one of the 3 numerical visual representations. So the 4 symmetric distributions, which this one is fairly symmetric, the mean is a good representation of a typical value of the data set. It can be thought of as a balancing point of the distribution. So if you look at the mean, where it's here in this dot plot, right where that red triangle is showing, it shows that it's a balancing point, right? It kind of balances out the data set, and we call that the typical value in a symmetric distribution. Okay, so here's another distribution, which is a little bit different. So if we look at the shape of this distribution, it's not symmetric, but in fact, this one is skewed. This distribution shows the salaries of professional baseball players in 2010. Do you think the mean is a good representation of the typical baseball salary for that year? So if you look at where the mean is located, which is the balancing point, that's where it's going to balance everything out. Is that a good representation of the typical baseball salary? Well, if you look at this person here who's making a whole lot, there's only one person all the way down there. That is probably an outlier. That's creating this tail in the right skewed distribution. You have all these people here that are also making a whole bunch, but most of them are actually here. And so where the mean is, do you think it's a good representation? Okay, so here's kind of a summary of symmetric versus a skewed distribution. So the mean represents a typical value in a set of data when the data is symmetric. But for skewed distributions, the mean is not a good idea for a typical value. And later on, I'll show you guys what would be a good typical value for skewed distributions. So here's how to compute the mean, which I think probably most of you have done before. Another word for mean, right, is the average. So to compute the average or the mean, you would add all the data values and then divide by however many numbers that you have in that data set. Sometimes though, for larger sets, it's super difficult to do this because it's just so time consuming. You would most likely use technology to do this. And I actually recommend you do this because with large data sets, the chance for making an error increases. So if you have a large data set, just go straight to technology to compute the average. Okay, so here's example 1, finding the mean. Suppose a sample of prices for 1 gallon of regular gas at 10 different gas stations in a neighborhood in Austin, Texas, is taken on one fall day in 2013. Find and interpret the mean. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different prices. That's doable to compute by hand. Technology is not necessarily needed for this one. So let's go ahead and compute this one by hand. So here's what the dot plot looks like for those 10 prices. What do you think a good estimate would be for the typical gas price? So where do you think would be the balancing point? It's always good to have an estimate of what your answer is before you actually calculate it. That way when you calculate it, you would know if your answer is correct or not. So I would think that the balancing point would maybe be around here somewhere. So let's go ahead and calculate the mean gas price. Okay, so here it is. I've added up or took the sum of all the gas prices, 10 of them. So because there's 10 of them, then you're going to divide by 10 in the denominator. So here's what the sum is. Divide by 10 comes out to 3.02. So interpretation. Anytime you interpret, or I'm always actually going to ask you to interpret your answer, just because in math you don't always want to get answers and not understand your answer. So here's the interpretation. So the typical, here's that word typical, the typical price of 1 gallon of gas at these gas stations in Austin, Texas was $3.02 on this particular date in 2013. So you see how this interpretation gives us an exact idea of what we found. That's what you're going to do every time you calculate something. Okay, so at this time, I'm going to ask you to pause the video and go find that spreadsheet that I had you guys create in Chapter 2, the one that we use data for goals scored by NCAA female players. Go pull up that spreadsheet now. Once you have that spreadsheet pulled up, in that spreadsheet, put your cursor on an empty cell, one that's blank, not on your data set. In that empty cell, you're going to enter in equals average and an open parenthesis. What this does is it tells, this equal sign tells the spreadsheet that you're going to be putting in a formula to calculate. Average is the mean that you want, that's what you want to calculate. And this open parenthesis, within this parenthesis right here is where you're going to put the data set that you want the spreadsheet to find the mean for. So now, after you have equals average open parenthesis, you're going to highlight the column of data. So that entire column of the goals scored, highlight that. If you have a heading above it, don't highlight the heading, just the values. So when you highlight that, you should have those cells appear inside your cell that you have the average for the calculation. Once you do that, you're going to close the parenthesis. So now your data should look, or your cell should have equals average, and in here should be the data set, the cells of the data set. Once you have that, then you're going to press enter, and then your mean should appear. So while you're doing your Pearson homework, what you could do to make it a little faster, if you don't want to calculate by hand with your calculator, you could pull open the tables, highlight the data set that they're giving you, copy it and paste it onto a spreadsheet. You could even just reuse this spreadsheet that we're talking about right here, and then calculate the mean that way from the Google spreadsheet, and then enter in your answer into Pearson. So basically just have a spreadsheet that's like a running document that you could reuse over and over for Pearson homeworks. Okay, so that was the center. Now we're gonna go on to talking about measuring the spread. So recall, the variability in a distribution can be measured by the horizontal spread. Why do we care? Because we need to know if most of the data is near the center or far from it. However, assigning a number to the horizontal spread is not straightforward. So anytime you calculate the mean, it's necessary to calculate the horizontal spread, just because the mean doesn't give you enough information to make assumptions or conclusions. Okay, so here's what I mean in example 2. The following histograms record the daily high temperatures in degrees Fahrenheit over one recent year at 2 locations. Okay, so 2 different locations. One is in Provo, Utah. The other one is in San Francisco. So if we were to look at the distributions and kind of figure out the typical value or the center, well, we can see here that both of these distributions are fairly symmetric, although the shape looks a lot different, right? The first one is a lot more spread out versus the second one is not so spread out. We're talking about horizontal spread this way. But because they're both symmetric, the balancing point will be roughly the same, which is kind of in the center. So you can see here that although the mean is maybe the same, it doesn't give you a whole big representation of what the data is like, because as you can see, they're completely different. Okay, so here's kind of like a summary of what we just talked about. Both distributions have roughly the same shape, which is symmetric. The actual center was for both 67 degrees in Provo and 65 in San Francisco. So you can see they're super close, right? That's the center. But the spread in both distributions is very different. In Provo, it's more spread out. Which means data values are far from the center. Versus in San Francisco, it's less spread out. Data values are closer to the center. So if you look at the graphs in Provo, Utah, you might have some temperatures that are super low at some points, really, really far from the mean. And then you might have some days where it's very, very high and also very far from the mean. However, in San Francisco, you don't have that spread, right? You don't have temperatures that are super far from the mean. They're all kind of clustered towards the mean in the center. So this is where we're talking about standard deviation. This is how we're going to measure the spread from now on in numerical data sets. So what is standard deviation? Well, it's a number that measures how far away the typical observation is from the mean. For most distributions, a majority of the data is within one standard deviation of the mean. So here's example 3, standard deviation. The graph below shows the distribution of the amount of particulate matter or smog in the air in 333 cities in the United States in 2008, as reported by the Environmental Protection Agency. The mean particulate matter is 10.7, and the standard deviation is 2.6 micrograms per cubic meter. So just as a refresher, remember when talking about sample and population, right? This histogram shows the results of a sample of 333 cities, which should be representing the whole population, all the cities in the United States. Okay, so also in the problem, they're telling us that the mean, this is a symbol for mean, is 10.7, and standard deviation is 2.6. So here's the question. Find the level of particulate matter 1 standard deviation above the mean and 1 standard deviation below the mean. Keeping in mind that the EPA says that levels over 15 micrograms per cubic meter are unsafe. What can we conclude about the air quality of most of the cities in this sample? I also just want to point out before we move further that a lot of the examples or a lot of what we do in this class, I'm going to try to relate it to our environment and how it's impacted and how we can use statistics to improve the environment. Okay, so in this space, we're going to be finding 1 standard deviation above the mean and 1 standard deviation below the mean. Recall that the mean is 10.7 and standard deviation is 2.6. So whenever you have these two pieces of information, from now on, I'm going to ask you to make a drawing. This way you can visualize what's happening. Okay, so also we're talking about a distribution that is symmetric, right? If you go back to the previous slide and look at the graph, you'll see that the shape is roughly symmetric. This is important to note. You should always look at the shape of your graph before proceeding. So based on a symmetric graph, this is the drawing that you're going to make. So remember, in a symmetric graph, where would the balancing point or the mean go? Well, that would go right in the center. Now if we want to get to 1 standard deviation above the mean, which would be here, 1 standard deviation above the mean, we're going to take 10.7 and add the standard deviation of 2.6. So that will get us to 13.3. If we wanted to get to 2 standard deviations above the mean, we're going to add another 2.6 to 13.3, and we'll get to 15.9. And if we want to get to 3 above the mean, we're going to add another 2.6 and get to 18.5. We're not going to go past 3 standard deviations, and I'll show you why in the next section. So now let's get the values below the mean. So if I want one standard deviation below the mean, I'm going to take that 10.7 and now subtract 2.6. This will bring us to 8.1. 2 below, subtract another 2.6, we're at 5.5. And then 3 standard deviations below the mean, subtract again 2.6, and we get to 2.9. This is the drawing that I'm going to ask you to do every time. Every time you have the mean and standard deviation, draw this out. It's going to be super helpful, trust me. So now let's answer the question. One level of particulate matter, one standard deviation above the mean is the value of 13.3. And then the level of particulate matter, one below the mean, is the value of 8.1. Okay, here's what the standard deviation formula looks like. I'm going to say up front, I'm not expecting you to memorize this formula. A lot of times in math, I feel like, I don't know if you've done this, but I've taken math classes where I was asked to memorize a whole bunch of formulas. I did, but as soon as I took the tests, I forgot them all and I didn't know anything. So really, I'm asking you in this class, instead of memorizing formulas, I'm going to ask you to understand them. That way, even if you forget, if you understand them, you could recall how to develop the formula. So here's all of the different pieces of the standard deviation formula. So the first thing that you would do in a formula like this is, you would go to the parentheses. So the parentheses is a value minus the mean. So you would go and take each value minus the mean. Why are you doing that? Because you want to know the distance from the mean, right? Standard deviation is talking about distance from the mean. Okay, second thing we want to do is we want to square the value. Why are we squaring it? Because distance is not negative, right? It's always positive. So we're doing that to make it positive. The next thing we're going to do is we're going to add all the squared deviations. So you would do that for all values, however many you have. And then you're going to take the sum of those. Next thing you're going to do is you're going to divide by 1 less than the sample size. So think of this as averaging this squared, right? So normally when you find the average of something, you divide by however many values you have. Well, we're going to do that same thing, except we're also going to take those values and subtract 1. Why are we subtracting 1? Because we're trying to find deviation from the mean. We're not including the mean. Okay, and the last thing we're going to do is we're going to take the square root to restore the original units. Because we squared it previously, we want to restore it back to its original units. And that's the standard deviation formula. So in this example, I'm going to show you how to manually calculate standard deviation. Of course, you could do this in computer software, but you still have to be able to interpret and understand what you're calculating. So here we go. Suppose a sample of prices for 1 gallon of regular gas at 10 different gas stations, same example, is shown here. So here's all the same 10 values of those gas stations. And now we're going to find the standard deviation. So standard deviation, calculated manually, takes a while. It's a very tedious calculation, which is why I prefer you to do it actually in technology or some calculator, because there's less error in that calculation. However, like I said previously, I want you to understand how it's calculated. Okay, so here is first column. These are all the values, the 10 values, those gas prices. The next thing you're going to do is within the parentheses, right in that formula. So what you're going to do is you're going to look to the parentheses. So here's this column right here where we're taking each of those 10 values, right? And we're subtracting it from the mean. So notice these are all the means. These are all the 10 values that are being subtracted from. Okay, so then once you do that, you're going to take that result and you're going to square it. So all of these results are now being squared to get to your positive value. Once you have it all squared and you should have all positive values, now you're going to add all these because this right here means the sum of. So now you want to take the sum of all these values. Once you have the sum of those values, that's this right here, you're going to divide by n minus 1. In this situation, n is 10, right? Because you have 10 values. 10 minus 1 is 9. This is why there's a 9 right there. So you're going to divide that and then take the square root, and then you'll have the standard deviation. So this part right here that's cut off because my table covered it, what it's showing, or what it said, I have typed previously, is that this standard deviation that you have here is actually slightly off. So that's what happens when you calculate manually. You might get a slightly off answer. Why? Because we're probably using rounded values, which we are. So this mean value of 3.02, this mean value is actually rounded. I didn't use all of the place values in there. So because we did that, in turn, our final answer became rounded. So that's why I suggest when you just put this all into technology, computer software, or a calculator, it doesn't round anything. So you get a more accurate answer. Also, keep in mind when you input your values for Pearson, if your answer is off by just a little bit, you're going to be marked wrong. So that's why you have to be super accurate and probably best to use Google spreadsheet to calculate this to get your answers for Pearson. And I'll show you how to do that in a second. Okay, so remember I said that we always need to interpret our answers. So here is our interpretation. So we got our mean at 3.02 or $3.02 and standard deviation at 0.09 or 9 cents. So here's the interpretation. At most of these gas stations, the price of a gallon of gas is within 9 cents of $3.02. That's what this standard deviation means. Okay, so go back to that same Google spreadsheet, the one with the goals scored by the NCAA soccer players. And now you should already have the mean in there, and now we're going to get standard deviation. So to find the standard deviation, go to another empty cell, maybe perhaps one right next to the mean. And now this time you're going to enter in equals STDEV open parentheses. And when you start typing this STDEV, it'll pull up a menu. Make sure you're choosing this exact one though that says STDEV. That's representing standard deviation. So then highlight your column of the data. After you highlight the column of the data, I want you to make sure that you close your parenthesis. Always get that habit. I didn't type it in here, but close your parenthesis and then go ahead and press enter, and you should have your standard deviation. So this is a variance. This is another form of showing variation or calculating variation. It's basically just the standard deviation squared. The standard deviation is preferred over variance since it has the same units. This is just changing it to a different form. So we're not going to use variance in this class. So you don't actually have to pay attention to variance. I'm just putting this slide here so that I'm pointing this out because this is in your textbook, but don't have to pay attention to variance. We're going to be focusing only on standard deviation. And that's the end of section 3.1. Hopefully this was okay. If not, please send me an email with your questions and I can help you through it.